Okay, so let's continue our discussion statistical mechanics. So till now, the examples we have considered or the situational system we have taken, we have always considered distribution of particles in compartments of equal size. So system consists typically whatever we have considered. So system consists of two compartments which are of equal size. Now, and where the principle of equal a prior probability is applicable. Now, if we have unequal size compartments or the compartments which are of not equal size, then what do you do in that kind of situation? So there, the probability of the equal a prior probability principle will not work. Okay, so that will not be equal. Okay, so suppose if I have two compartments of a size, one is bigger than the other, and again with the same condition, if I throw a particle, it has to go any one of the compartment, then the compartment which has larger size will have higher probability of getting that particle into it, right, compared to the other one. So now how do I proceed with these compartments of unequal size? So there we bring concept of cell. Okay, so now idea is what we will take n distinguishable particles as mentioned here, okay, and are to be distributed in k compartments of unequal size. Okay, now let's try to draw one big compartment. Okay, so sorry, a big system which consists of sort of, okay, so this is my system now. So it has got unequal compartments. So I will try to draw, let's say, one line like this, one like this, okay, one compartment could be like this, next compartment, okay, not necessarily straight lines, it could be any size, but I'm just, sorry. Okay, just assume. Okay, so now these are my compartments which are of unequal size, and just as simply for our naming, let's say there is only, so this is my compartment 1, so I name it compartment 1. So this is 2, okay, so this is 3, 4, and then say the last one is k. Okay, in between, let's say I have the ith one. Okay, so these are my unequal compartments. So what I do now, because I cannot now, I don't know what exact probabilities, and I don't know whether the probabilities are equal or not, because compartments are of unequal size. So if I throw distinguishable n objects to it, I only know that probably the larger the compartment size, the probability of getting the particle into it will be higher. Only that much I know. Okay, so to apply whatever we have learned earlier, so what we will do, we will divide these compartments into very small size cells. Okay, so how do you make those? It's like, I divide these compartments of like this small cells. Okay, so let's say another compartment which I take like this. Okay, so I just continue doing this. So only thing which I have to remember here is that, so these compartments which I have just drawn, these compartments, or this cells, small cell, these are of equal size. So cell in, let's say, compartment 1 is equal to any other cell or any other size. So size of the cell is same. Okay, these are same size, whether it is in compartment 1, 2, or any ith compartment, k compartment. So in that way, now what happens? So I can apply now, because now each cell in different compartments are of same size. Okay, so now I can apply the principle of equal a prior probability. Okay, now depending upon the size of the compartment, now the number of cells in the compartment will vary. Okay, so I have now total n distinguishable particles, and I have this k number of compartments. So let's say I have G1 number of cells in compartment 1 and G2 number of cells in compartment 2. Similarly, G3, okay, GI number of cells. Okay, now this is GK. Okay, so idea is what? Now I have to distribute these n distinguishable particles in defined compartments, where each compartment has got now certain fixed number of cells, and each cell is of equal size. Okay, so now let's try to, so what we are trying to achieve here is we are trying to calculate the number of ways I can distribute these n particles in k compartments of unequal size. That's the, okay, so even though the compartment size are unequal, so by introducing the concept of cell, so I have somehow, you know, managed to apply this principle of equal a prior probability. Okay, now so I just simply keep this little aside, and I need to have a little bit of space here. Okay, so let's just I keep it a little bit aside, or make it a little small if possible. Resize. Okay, so I just made it a little small. Okay, so then I keep it just aside. Okay, so what I will do now here, so I have now n, and let's say, so let's talk about so our idea is to distribute, let's say, n distinguishable particle in k compartments, whereas the n1 particle, let's say, go to the compartment 1. Okay, and n2 go to compartment 2. Okay, so similarly I can have ni going to ith compartment and nk number of particles going into k compartment. Okay, so kth compartment, this is second compartment, this is first compartment. Okay, now since I had total number of n particles, so I have to now choose n1 number of particles. First thing to do. Okay, so how many ways I can choose this n1 number of particles from the total of n particles? So that will be given by, so total number of ways I can choose this n1 number of particle from total of n particle is given by, so ncn1. So then this is will be n factorial by n1 factorial n minus n1 factorial. Okay, all right, so this is, so these many ways I can, so these many ways I can choose first n1 particles from out of the total number of n particles. Okay, now what is our idea? These n1 particles are there, so we are considering that macro states. Okay, so this will give you one macro state, right? So n1 going to compartment 1, okay, n2 going to compartment 2nd, similarly ni going to ith and the nk going to n. So this is one macro states. Okay, so now how do I choose n1? So this is given by this particular formula that we have just discussed. Okay, so now so okay, so now consider out of these n1 particles, so out of these n1 particles, let's consider the first particle. Okay, the first particle we are considering. Okay, now if you consider that particle, okay, let's again bring back this okay, so let me just probably zoom it here. Okay, so okay, so we have the first particle now. So there are G1 number of cells in this compartment 1. Okay, so the G1, so the, and we are considering these are classical particles. So this particle can go into any one of the cells. Again, these cells are very small size, but these are all cells are of equal size. Okay, and there are G1 number of, so G1 number of cells in compartment 1. So this first particle can go any one of the cells. So how many ways I can arrange, so I can have the particle in the compartment 1? So there are G1 number of ways I can have the first particle. Okay, G1 number of ways I can arrange the first particle. Okay, so now take now the second particle. Okay, so first particle, let's say it has gone any one of this, let's say it has gone to this cell. Okay, now take the second particle. Okay, now second particle also can go into any one of these cells. So how many ways I can arrange both the particle, first particle and second particle in G1 number of cells? Because in both the cases, both the particle can go to any one of the cells, and a single cell, there is no restriction on these cells, the how many numbers of particles it can occupy. It could be 0, it could be 1, it could be 2, it could be any number. These are classical particles. Okay, so then number of ways I can arrange or I can have this first particle and second particle in compartment 1 having G1 number of cells. So I will have G1 for the first particle and G1 again for the second particle. So the total number of ways I can distribute or I can arrange these two particles, first and second, inside this compartment 1 is G1 number. See, there are how many particles are there? There are N1 particles. So third particle will go, it can go to any one of the G1 states or G1 cells. So like this, I can have third particle G1, so it will keep on going. Okay, so then this will go N1 times. Okay, so I can write, sorry, G1 to the power N1, right? This is N1 times. So this gives you what? Number of ways I can distribute N1 particles in this compartment 1. Okay, so then, so total number of ways, how do I choose this N1 particle from the total of N particle and distribute them in this compartment 1? Then I have just simply multiplication of these two, right? So the number of ways, so where I can have N1 particle to be distributed in this compartment, first compartment. Okay, so that will be given by N factorial, N1 factorial, N minus N1 factorial. Okay, so multiplied by G1 to the power N. Okay, so what does it give? Let's again come again. Okay, so this gives you, okay, so this gives you the number of, this formula gives you the number of ways to distribute N1 particles out of N particles in compartment 1 having G1 number of cells. Okay, so this is very crucial. Okay, so now let's continue. What will happen in the second compartment? Okay, so now if we just so now the second case which you need to consider, the N2 particles in compartment second. Okay, so again this the second compartment, this the second compartment as well, the second compartment, it has got how many? Second compartment has got G2 number of cells. Okay, and we have to now distribute N2 particles in this. So now I have to select N2 from N2 number of particles after distributing N1 in compartment 1. Okay, so in that case, so already now the total number of particles we are left with is N minus N1, right? Because N1 I have already redistributed in the compartment 1. So out of this total particles, we have to I have to choose now N2 number of particles. Okay, so how many ways I can choose them? That will be given by this particular formula. Okay, so this will be given by N minus N1 factorial given by N2 factorial. Okay, here N minus N1 minus N2 factorial. So this many ways I can choose N2 out of this N1 minus N2. Okay, now again if you come back to the you take like first particle, out of that N2 particle you take the first particle. Okay, so again again similar to the earlier case, so this particle can go to any one of the cells which are present in this compartment 2. And how many of them are there? Are G2 number of cells present. So how many ways I can arrange this particle within the compartment 2? So there are G2 number of ways I can arrange. Similarly, if the second particle comes again, that can go to, so if I combine first and second particle in the compartment 2, again there is G2 into G2, okay. Ways I can arrange these two particles in the compartment 2. Similarly, I can have, if I keep on adding n2 number of particles, so this will give me, so this will lead to, this is like this multiplication will go all n2 times, okay. So total will give you G2 to the power n2. So how many ways now I can distribute this n2 number of particles to be which to be chosen from this n1 minus n1 number of particles, and then distribute them in a compartment second, or the names which have given second compartment having G2 number of cells of equal size. So that will be given by this total number of ways n minus n1 factorial divided by n2 factorial n minus n1, okay, multiplied by G2 to the power n2. So this exercise, so again just to remind ourselves, what does it represent? So this gives you number of ways that I can distribute n2 number of particles out of this n1 minus n minus n1 particles to be distributed in the compartment 2 having number of G2 number of cells. Okay, now this exercise we can continue. Okay, we can take third compartment where there is G3 number of cells and then n3 number of particles to be distributed. We can continue up to ith particle, ith compartment, and then to the kth compartment. Okay, if you continue like this, so we will achieve, okay, so we will get a mathematical expression like this. So let me just highlight here. Okay, so we'll get this. So what does it mean? Okay, so what does it give? So it gives you total number of ways placing n particles all in all the 1 to k compartments in such a way that n1 particles or n2, n3, ni, nk particles go into the compartment number. So n1 goes to compartment 1, n2 goes to compartment 2, ni goes to ith compartment, nk goes to kth compartment. So what we are trying to do, so total number of microstate corresponding to this macrostate, as I told you, this n1, n2, n3, n4, all this nk, so it gives you one macrostates. Okay, total number of microstates means how many ways you can distribute the particles or arrange them, group them within this macrostate is given by this particular expression. Nothing else. We have to multiply all the expression that we get. Okay, similarly. Okay, now if we remember, if you look at this, you know that this total number of particle n is going to equal to n1 plus n2 all the way, keep going, ni all the way till nk. So this expression here, n1 minus all these things, will give you n. Okay, if you sum them up, so that's what it is given here. See here, this n1, this is n. So this in the denominator, this term will give you 0 factorial. That's what we have got, 0 factorial. Okay, which is going to 1. So therefore the total number of microstates for this n1, n2, and all the way nk macrostate is given by this particular formula. Okay, so this is possible only if we introduce the concept of cell. Okay, where we have considered where we have these compartments of unequal size. Okay, so and this G1 represents the number of cells in the compartment 1. Similarly, Gi represents number of cells in the ith compartments, and each cell across the different compartments are equal. Okay, so we can extend our discussion and write this expression in a very short notation like this. Okay, so this W is thermodynamic probability, or you can think about number of microstates for a given macrostates. Now let's simplify the problem. Means what we have considered earlier, that compartments of equal size. Okay, so what, just now let's try to calculate number of microstates if we, for all these k compartments, if all of them are equal size. So then I need not introduce the concept of cell. So I can assume once the entire compartment has one cell. Okay, if you think about like that, so gi is going to be your 1. Okay, so if gi, you can think about 1 now. Okay, so the so if you have distribution of particle equal size compartments, so gi is 1, then I don't need to use gi. Okay, so gi, simply the other expression will remain n factorial divided by this 1 by product of this ni factorial. Okay, and the probability of that macro state, we know this is thermodynamic probability divided by the total number of microstates gives you the probability of the macro state. And in this case there are k compartments of equal size, so total number of microstate will be k to the power n. Okay, so in case if for unequal compartments, so unequal compartments, so each compartment will have, let's say, G1, G2, G3 like that. So total number, so I can assume, so for unequal compartments, so I can have G1 number of cells in the first compartment, G2 like that, GI, keep going, GK, all the way, let's say capital G. So if, and we, so that this total number of microstates will be decided by this. Okay, so we'll do an example, then it will be even more clear. Okay, so from this, let's just summarize what we have obtained now. So for distribution of n particles in k compartment of unequal size, because we cannot apply this principle of equal a prior probability, so what we have done, we have introduced the concept of cell, where, so these compartments of unequal size, so we have introduced the concept of cells. Okay, and the cells are very small size boxes, if you think about, within the compartment, which are equal size across the compartments. Okay, so and so then we had, depending upon the number of size of the compartments, we had different numbers of cells. So if your size of the compartment is large, then it's of course it will have more number of, or higher number of cells. Okay, then we started distributing the particles. We have seen how many ways we can choose the particles from the total particles, and then how do you distribute within the cells, within the compartments, and we have obtained finally we have obtained the different number of ways we can distribute the n1 particles in compartment 1, n2 particles in compartment 2. Okay, similarly nk particles in k compartments of unequal size. Okay, that means totally I eventually have calculated the number of microstates for a given macrostates. Okay, now let's try to understand this some more using an example. Okay, so the given problem here is that 8 distinguishable particles are to be distributed in 2 compartments of unequal size. Okay, so again, if we go back to our earlier discussion, so we have 2 unequal size compartments, let's say. Okay, so we have 8 distinguishable, so n is equal to 8. Okay, and the first compartment is further divided into 6 cells. Okay, so I think I should have drawn the first one to be a little bigger than that. Okay, okay, so let's try to, okay, so like just to have some kind of consistency with the problem. Okay, so so the first so the compartment may not be up to the scale, but let's see. Okay, so it has divided into 6 compartments. Okay, 3 4 5 1 2 3 4 5, there could be 6. Okay, so and then this is divided into 2 compartments. Okay, so don't worry about the scale of or the size of these cells, but in principle, okay, so let's in principle this cells, okay, this has to be equal. Okay, okay, this is not up to the scale, but this is equal. Okay, so the 8, so then this is compartment 1, this is compartment 2, let's assume. So first compartment is further divided into 6 cells, and the second compartment into 2 cells of equal size. Okay, now calculate the probability of the macro state 6, 2 and 4, 4. Okay, now first we need to, so the probability of a macro state is given by what? The thermodynamic probability divided by total number of micro states. So first let's write a general formula. So W N1, so we already know Nk is given by, so the n factorial divided by n1 factorial, n2 factorial, all the way nk factorial multiplied by g1 to the power n1 all the way keep going g k and k. Okay, okay, so now in this case I have only 8 particles, so n is equal to 8. Okay, how many compartments? So the k is equal to 2 now. So let me just get this 8 number here. Okay, so n is 8 here. Okay, so n is 8 here, sorry, then the k is 2 here, 2 number of particles. Okay, and g1 here is 6 and g2 is here 2. Okay, so first of all let's calculate w 6 2. Okay, n1 in the 6 of them. Okay, so n is here 8 factorial, okay. N1 is 6 factorial, okay, and n2 is here 2, so 2 factorial. Okay, so multiplied by g1 is a 6 to the power n1 is here 6 and multiplied by g2, so g2 is 2 to the power, so this was nk, so the g to the power, so 2. Okay, so this gives you my number of microstates for that, or the thermodynamic probability. So the probability of the macrostate can be calculated 6, 2. Okay, so this will be given by, yes, so let's try to calculate the total number of microstates for this. Okay, so the total number of microstate can be calculated. So let's try to erase this. So the total number of microstates, so it will depend on total number of cells. Okay, so now in the compartment 1 there are 6 cells, in compartment 2 there are 2 cells. Okay, and each compartment, so there are 2 compartments, so there are this many total number of cells. Okay, and this will be to the power n. 8 will give you total number of microstates. Okay, so this will give you total number of microstates. So the probability of the microstates, this 6, 2 will be given by the thermodynamic probability that we have obtained, 8 factorial by 6 factorial, 2 factorial, and 6 to the power 6, 2 to the power 2, multiplied by 1 by 6 plus 2, 8 to the power 8. So if you do calculate out this maths, so it will result in 0.31. So sorry. So if you carry out the maths, okay, this is a simple multiplication, so you will get 3.11. Okay, so if you proceed in the same way, so for the second case 4, 4, so you can see all the things are given here, so it's a simple maths to carry out. So you will get probability for 4, 4. Okay, so only just few numbers here and there will change. So in that case you will get 0.0865. So this gives you the probability of occurrence of the microstates 4 by 4, 4, 4 and 6, 2. So from these two probabilities, you can see that just looking at the probability of the magnitude of the probability or the value of the probability, you can see that 6, 2 is more probable compared to the 4, 4. So in this way, we can calculate the probability of a macrostates. Okay, first of all, you have to calculate the number of microstates for that macrostate, and then you have to calculate total number of microstates. Okay, so yes, we shall stop here.